Hey, I wanted to talk briefly about chapter 5, numbers 12 and 13, which I had originally assigned as homework, but I decided since we are all pretty tired and have a lot going on, including me with a cat walking on my iPad, that I'd do these this year and we'd take a look at them and talk about intersections and unions and how we check that something is a subfield. So the setup for both 14 and 15, this is chapter 5 in Bob Redfield's Abstract Algebra, a Concrete Introduction, looking at numbers 12 and 13 here. The setup is we've got a field E, and we've got subfields, K and F contained in E. And we want to know in 12, is the intersection a subfield? If so, prove it. If not, give a counterexample. And in number 13, we want to know, is the union a subfield of E? If so, prove it. If not, give a counterexample. So I'm going to do 13 first, talk about the union first. And I'm going to pick a couple of fields that I'm going to use here. So I'm going to pick my K to be, I'll write it this way. It's going to be things of the form A plus BI, where A and B are rational. So we talked about that one in class a little bit. And we're going to look at F. F is going to be A plus B square root of 2, where A and B are in Q. We talked about this one really, really briefly in class, and it's very similar to some that you've looked at in the earlier homeworks in this chapter. And I want to think about some elements that are in the union of K and F. So if I look at K union F, it's all the stuff that looks like, I'll just write it colloquially, it's stuff in K or stuff in F. Let's even write it this way. So it's going to be like elements that are in K or F or both. And so let's notice a couple things that are in there. I mean, like rational numbers are going to be in there. So A in Q is going to be in there. If I look at I, well, that's in K, so that's in there. And if I look at square root of 2, that's also in K, so that's in there. Or sorry, that's in F, so that's in there. And I need to know if this thing's a subfield. So I'm like, well, one of the things I'm doing is I'm checking, does it have 2 elements? So it's got 2 elements at least. Sure, we said I and 2, and 0 and 1 if we want to. We've got some stuff in there. Then if I think about closed under addition, I'm looking at this element. I'm looking at I plus 2. And I have to ask myself some questions about this. Is it in the union, which means is it in K or in F or maybe both? Well, if it's in K, I'm supposed to be able to write it as A plus BI. So it's like root 2 plus I. Is that equal to A plus BI for some rational A and B? And the answer is no, because we've got that square root of 2, which is irrational. I can't write it as a rational number. And it's also not of the form C plus D root 2 for some rational C and D, because I is not a rational number. So it turns out this is not closed under addition, because if I try to add I and root 2, I get something that's not in the union anymore. So this fails to be closed under addition. Therefore, it's not a field. Not a subfield. Well, it's also not a field, but it's not a subfield of the complex numbers, which are my big E. And I want to do the intersection. So this was number 13 in green here. For number 12, I want to think about, I'm going to use the same two fields here as an example, just to see like, well, if it's not going to work, maybe this is a counterexample. But if it works, it might give me some insight into whether it's going to work in general, or if I had something special going on here. So we look at K intersect F with the same K and F. That's the set of elements that are in K and in F. It's got to be in both of them. So it's elements where there exist rational numbers A, B, C, and D, satisfying A plus BI in the K part looks like C plus D root 2 in the F part, which means that, well, I can't write BI as a C plus D root 2 part. That's what we established before. So that means that B is 0. Similarly, D has to be 0. And then once we've killed off the B and D parts, we're like, okay, well then for these to be equal, A has to be C. And what that means is that K intersect F is actually just with the rational numbers. It's like, okay, we can just make the rational numbers, and that is a field, which is a subfield of the complex numbers. So my thinking for number 12 here is that this might be true, actually, that if I intersect fields, I get another field. So let's see if I can prove it. Let's try proving the claim, proof of the claim. K intersect F is a subfield of E with the setup that we've got. K and F are subfields of E. So two elements. Since K is a subfield. Okay, sorry, the cat's walking on the iPad. Go away, cat. Since K is a subfield of E, 0 and 1 are in K, right? It's got addition and multiplication, and it's closed under those operations. It has inverses. So I know 0 and 1 from the bigger field E have to land in K. And similarly, F is a subfield. So I have 0 and 1 are in F. And that tells me that 0 and 1 belong to both K and F, which means that 0 and 1 are in the intersection. So I've got at least two elements in here. All right, if I go through the rest of the subfield theorem, I need closed under addition, closed under multiplication, and closed under taking inverses for elements. So let's see. Closed under addition, let's let, I don't know, alpha and beta be elements of K intersect F. That means that alpha and beta are both in K, because K is a subfield, and this has to be in the, well, it's not that K is a subfield, it's that it's in the intersection, so it's got to be in K. And K is closed under addition. So alpha plus beta also has to be in K. And then similarly, alpha plus beta is in F, because alpha and beta are in F. F is a subfield of E, so it's closed under addition. So when I add up alpha and beta, I land back in F. Closed under multiplication is going to be the same thing, right? If A and alpha and beta are in the intersection, then alpha and beta are in K. So alpha beta is in K because it's closed under multiplication as a subfield. And similarly, we're going to get alpha beta is an F. And that tells me that alpha beta lands back in the intersection because it's in both K and F. I think I forgot to write that up above, but alpha plus beta landed in both K and F. So alpha plus beta is also in the intersection, K and F. And it's going to be really similar for the others. If I look at additive inverses, if I take alpha in the intersection, then alpha is in K, which implies negative alpha is in K because K is a subfield. Similarly, alpha is in F, which implies negative alpha is in F because F is a subfield, so it's closed under taking additive inverses. So negative alpha is in K intersect F. Cool, so I can do additive inverses. And the very last thing is multiplicative inverses for non-zero elements. Multiplicative inverses. So if I have a non-zero alpha in K intersect F, alpha's in K means that alpha inverse is in K because K is closed under taking multiplicative inverses. And alpha in F means that alpha inverse is in F. So it's still non-zero in F, and F is a subfield. It's closed under taking additive inverses. And therefore, alpha inverse is in K intersect F. And that's the end of our proof. We've shown that all 5 things in the subfield theorem hold, and we get that K intersect F is a subfield. Where that broke for the union is I don't ever get to say, like, I could take 2 elements in the union, but I don't necessarily know that they're both in K. So I can't use the fact that K is closed under addition because one of them might not have come from K. And that's where things go a little bit funky here for those. So that is the gist of how you do number 12 and 13. I hope that was useful to you, and hope you're having fun with these fields. All right, let me stop recording.